So the topic of today is going to be holographic superconductors. So this has been a hot topic, and well, it triggered much of the interest in these condensed matter applications. So let me remind you what a superconductor is. So we have a normal conductor, a metal, and we introduce an external electric field. Then the current, as a function of time, will start growing, and then it will saturate at some value. No? And then this value is determined by the conductivity. We have a superconductor. Then the current just grow with time if we keep the electric field. And if we turn off the electric field, then in a normal metal, the current will just decrease. And in a superconductor, the current will remain constant. This is when we set the electric field equal to 0 after some time. So a superconductor can support a current without dissipation. So you can see this in the conductivity. If we do a Fourier transform of the Ohm's law, then the current as a function of the frequency is proportional to the AC conductivity and the Fourier transform of the electric field. And then in a superconductor, this conductivity is singular at 0 frequency. So there is a real part, which is a delta function, and then there is a pole in the imaginary part, and the coefficient between these two is fixed by Kramer's chronic relations. So this is just causality. Okay. So I told you before during the lectures that you will also have this behavior. You have a system with translation invariance that will be a perfect conductor rather than a superconductor. But you can distinguish between the two if you look at other effects, like if you consider a magnetic field. A magnetic field in a superconductor cannot penetrate. So if you try to introduce a magnetic field, it will try to go around the superconductor. And this behavior is different in a perfect conductor. So in condensed matter, the standard model of superconductors, if you want, is BCS theory. That stands for Bardeen-Koper-Schrieffer. So the idea is that you have the electrons in your material, and then there is an attractive force between them, which is usually due to the phonons in the lattice. And this attractive force makes these electrons pair if you have the right conditions, no? At low temperatures and so on. And when they pair and they form a Cooper pair, then you are in the superconducting phase. So BCS makes very precise predictions about this state. For instance, there is a gap for excitations, which correspond to breaking these Cooper pairs. This gap at 0 temperature is fixed to be something of the order 1.8 Boltzmann constant times the critical temperature. And as the temperature reaches the critical temperature, this goes like 3 times. The gap goes to 0 with a concrete power. So anything that I'm just putting to show that you have very precise predictions from BCS theory, and everything that doesn't fit within these predictions then is called an unconventional superconductor. Okay. And then sometimes this includes other superconductors that also have Cooper pairs, but maybe they don't form a singlet state, but they form some p-wave state or they have other orbital angular momentum. So some of these unconventional superconductors are interesting for technological applications because they have a high Tc superconductivity, meaning that this critical temperature is much larger than the ones you will have in a conventional superconductor under the same conditions. So for instance, the record, I think now, is at atmospheric pressure. Is of the order of 133 Kelvin. Okay. So this is much larger than the usual ones that usually need liquid helium to cool them down to the superconducting phase. This may need also liquid nitrogen only. So I must say that you can have conventional superconductors when the critical temperature is very large also, but you have to go to some extreme conditions, for instance, really high pressures. I didn't tell you how this depends on external parameters, but this can vary in different models. So I think there are some conventional superconductors when you can reach critical temperatures even higher than this one, but at very large pressures. Okay, so in particular, this high Tc superconductivity appears in some materials that are known as the cuprates. And then, well, there is no satisfactory description of these materials from the microscopic point of view in condensed matter. So they are effectively two-dimensional, and then they look like strongly correlated. No, if you look in the phase diagram, there is a region of the phase diagram where they have this strange metal behavior we were talking about yesterday. So there is some parameter which is doping, which is related to introducing some impurities in the material. And then there is temperature. And then the phase diagram has some superconducting dome. And there is some region here where you have the strange metal. So this linear resistivity. So this motivated Arnold, Herzog, and Horowitz to study these unconventional superconductors using holography. No? They are going to be unconventional because this Cooper pairing is something that happens at weak coupling, and in holography deal with strongly coupled materials directly. Yes. Uh, well, you have a, yes, depending on the region, you can have something that looks like a Fermi liquid, or there can be a region here where you have some magnetic material. So, but this can change from material to material. But this part is more or less universal. So, okay, so these holographic superconductors, they have some aspects that are similar to Ginzburg-Landau models. If we talk about the formation of the superconductor, the superconducting phase. So the idea is that when you're in this superconducting phase and you're forming these pairs, then there is an operator, which is like two fermions that has some non-zero expectation value. No? This will characterize the superconducting phase. And well, as you see, this will break spontaneously the E1 symmetry of electromagnetism, no? Because these two have the same charge. Now, one can describe this, the formation of this condensate, introducing some scalar operator, which is roughly this bilinear fermion. And then there will be an effective potential for this operator, which is now bosonic. So one can write the effective potential as some mass term and then some quartic interaction. And then this mass term depends on the temperature. And close to the critical temperature, it's going to 0 linearly. So from that, you have that the mass will be positive if the temperature is above the critical temperature, and then the mass will be negative if the temperature is below. So you go from a potential for phi that looks like this to a potential that looks like this. This will be 0. So you have the usual spontaneous symmetry breaking with the Higgs mechanism. So, sorry? It's a second order phase transition in this description. So holographic models are similar to this Ginzburg-Landau, but you don't have an effective potential like this one. You may be able to describe the formation, this transition, by something more complicated. Some people have tried to do that, actually. And then you can have here different powers of this phi. I should say that in reality, when people is doing holographic superconductors, they are doing holographic superfluids, because we are taking some operator which has some charge, but is charged under a global symmetry. No? Because we have a map between the global symmetries in the boundary and the well, you have a system which microscopically can have fermions charged under the symmetry you are looking at, but you are looking at gauge invariant operators which are bosonic, like this phi. For instance, if you have, suppose you have something like a QCD-like theory, no? You will have your quarks. Then you will look at an operator which will be like Q bar Q. Well, Q bar Q, no. But yeah, you will need something of this form that can compensate the indices. Sorry? Yeah, there will be a scalar with two indices, maybe, and then a fermion, and then you can form a gauge invariant operator, and this will have charge too. So this will be a possible, and if this gets an expectation value, then it's analogous to this situation of the Ginzburg lambda. So your theory can have fermions and scalars, and they can form a condensate. This is just an example. I'm not going to talk about any particular gauge theory. But the thing is, the symmetry that is broken is global. So the idea is that you will couple this holographic model to E1 electromagnetism. Okay, so then you will have that your Lagrangian or your action will be the CFT action, or that you describe using holography. And this depends on some A mu, which you treat as an external source. And then what you do is you add a Maxwell term for this guy. Okay. This will be the field strength of this field, and then G square will be small. So then you treat this in a perturbative way. So I'm going just to talk about the calculation of the CFT part. No? This part is standard. If you want, what you will see is that you have a photon. This photon couples to a current operator of the CFT. And then this current operator, the propagation of this current operator is described by the two-point function of the current. And then again, you emit another photon. So this contributes to the self-energy of the photon. And here you have the gauge couplings. Okay, so if you want to describe the superconducting behavior, you have to do this part as well. But I'm going to focus only in the calculation of these two-point functions. Okay. So the starting point is the ADS Reisner-Nordstrom that we saw yesterday. So let me just write the metric to remind you. This describes a charged black hole. So it describes some state at finite density in the dual field theory. And, well, we are going to introduce a scalar field. So and then this scalar field is charged under the gauge field that we have in this solution. Okay, so this covariant derivative involves a gauge field that is here. I can write it as well. The gauge field looks like this. Okay, so you can derive, well, so here describes the charge state, and then in our theory there is a scalar operator which is charged under this gauge field. That is like this situation. We can think of this scalar operator as dual to this kind of bilinear. And then we want to see is if the solution where we just have charge, no condensate, is stable. So we look at fluctuations of this scalar field. Then we right of the metric and the gauge field. But is the same as yesterday. So you have Einstein gravity coupled to Maxwell. And on top of this, you add this part. Yes. Yes, we are looking now at this, which corresponds to a state with charge density. But so far, we are in this phase. Okay, so it's like there is no condensate. And now we can change the temperature here and see if we are going to go to this situation. Okay, so we're going to see if we go from here to here by looking at the fluctuations of this scalar. So if we expand in plane waves, the equation for the scalar will be something like it will be a second order equation in the radial coordinate. And it depends on the mass, the functions that appear on the metric, the frequency, the momentum, etc. Okay, so here you have the charge of the scalar under this gauge field. So close to the boundary, when r goes to infinity, the scalar field has an expansion, which is given by two different powers of the radial coordinate. No? This is the dimension of the dual operator that I remind you is related to the mass in this way. And then close to the horizon, the scalar field has an expansion in waves. So we saw a little bit of this yesterday. There is an ingoing wave and an outgoing wave. So dynamical modes in the dual field theory correspond to setting C1 equals to 0. So otherwise, we will be introducing some explicit breaking of the symmetry. And then in order to compute the physical modes, we set the outgoing coefficient to 0. And this fixes the, in principle, if we do this, then there is no solution. The reason is that, maybe, yeah. The reason is the following. We are trying to solve a second order differential equation, linear with regular points, and the boundary and the horizon are these two regular points of the differential equation. And there are two independent solutions here and two independent solutions here. Okay, so these were the C1, C2, the in, A out. And then there is, if you solve the equations, there is a transformation that takes you from these two to these two. So if you kill one here, then this will be a combination of these two, a precise combination of these two. But if now you kill this other one, in general, there is no solution. There is only a solution for some discrete values. Of the frequency. Okay, and this gives you what is called the quasi-normal modes. So if you plot these quasi-normal modes in the complex frequency plane, usually they are located on the lower half plane at some distance from the real axis, which is of order of the temperature. This is the typical situation when you don't have any match, for instance. And then the fluctuations of the scalar for one of these quasi-normal modes will have an oscillating part with time, which goes like the real part of the frequency, and an exponential part, which goes like the imaginary part. So these modes are stable if the imaginary part is negative. If the imaginary part is positive, then they will start growing exponentially in time. So if you take this background and you start changing the temperature or the charge, then these quasi-normal modes will start moving in the complex plane. And then it will happen that one of them or some of them will approach the origin and then cross to the upper half plane. Okay, so you can study this numerically, or in some cases you can do some approximations and do it semi-analytically. But there is a value of the temperature where one of these modes reaches the real axis. So that will be the critical temperature. After that, you have an instability, which means that this background with no scalar field is unstable. So now you should find a new solution. And because the scalar mode is the one that is growing, the new solution will have a non-zero scalar field turn on. So that will give you the spontaneous symmetry breaking. Well, if you allow the frequencies to be complex, there is really no distinction between doing it in the Euclidean or not. So, no, because you will just change this omega by I omega, no? If you do it in the Euclidean. So then what you'll do is just rotate this plane. Say it again. Finite? Yes, right. Yeah, this mode, the unstable mode, will be finite in the Euclidean. So the ingoing mode, but the unstable one will be finite in the Euclidean. The ingoing, yeah. Okay. Yes. Well, for concrete models, you fix delta. Usually, no? HHH did it for D equals 3. And then I think delta was maybe 1 or 2. But in principle, you can do this for any relevant operator. The lower is delta, the easier is to get the instability, and the higher will be the critical temperature. Usually. Yes, any charge operator in principle will have this behavior. If you do Reisner-Nostrom, if you go to the extremal solution of Reisner-Nostrom and you look at a charged scalar field, then you will see there are instabilities there. So, the critical temperature? Or so this is the relation between M and delta. Yeah. Yes, so for particular models, you have a particular choice. But this is the general situation. Yeah, M squared is -2, I think, in this situation, maybe. For delta equals 1, or delta equals 2. So, but this is just a particular choice. No? There are many other examples where you have different deltas and D. Okay. So the issue to give a lecture about this is that most of the calculations are numerical. So I cannot show you a lot of things, but I can show you something in a toy example. So I'm going to do a toy example, which will be a holographic superconductor. And then you can do everything analytically. But you shouldn't take it very seriously. It's just to show how things work. So I'm going to make some simplifications. The first one is that I'm going to take the gauge field and the scalar to be probes. So the gauge field in the bulk and the scalar are going to be probes. And by this I mean that they do not back react on the metric. Okay, and this you can see as the large charge limit. Okay, I mentioned this in the last lecture, that you can take a parameter such that this is very small. The back reaction is very small. So the action of the gauge field and the scalar is just the usual thing, Maxwell. So this is, and then there is the scalar action that I wrote. Okay, and then I'm taking this Q to be very large, and that makes back reaction on the metric. So that's the first simplification. The second simplification is I'm going to be at 0 temperature. Okay, so this means the metric is ADS. Now, if I do that, I won't be able to do much. So I'm going to introduce a hard wall. So I'm going to declare that the space ends at some value of the radial coordinate, Rm, which is related to some mass scale, M. So this is like a very rough toy model where instead of the horizon, I have this hard wall. And then I neglect any effects of having a different metric because I have a black hole and so on. So I only consider the dynamics of the scalar and the gauge field. No, so this is, if you have the black hole and so on, then you have to do numerics because you don't know the analytic solutions and so on. So I'm just doing this because I can do it analytically. So it's just a toy model. But then you will see that you capture the physics. It's just for pedagogical reasons. So this is the equation of motion of the gauge. And this is the equation of motion of the scalar. And then I will work in a gauge where the radial component of the scalar is 0 the time. So this is my gauge choice. And we start setting the scalar 0. Okay. Then the equation for the gauge field is very simple. I'm only turning on this time component of the gauge field. And the equation of motion is this thing. Okay. In principle, I have two solutions. Now, I told you that I have some kind of hard wall, and then here the boundary. So I'm living in this space. And I have to specify the boundary conditions for the fields on this hard wall. So something that will look like the black hole will be to set the value of the gauge field at the hard wall equal to 0. Okay? If you have a black hole horizon, you impose this condition for the gauge field at the horizon, because when you go to the Euclidean, you will have a regular solution. So this corresponds to the thermal equilibrium. But for me, it's much simpler to take the condition that the flux at the hard wall is 0. So the field strength at the hard wall is going to be 0. This is going to be the condition I take, which just means there is no behind this. And then with this boundary condition, the solution for the gauge field is just that it is a constant. It's equal to the chemical potential. So now I can look at the equation for the scalar field. In the presence of this gauge field. So the equation takes a form like this. And then, again, I have two solutions. I have to impose boundary conditions on the hard wall. If you had a horizon, you will impose the ingoing boundary condition at the horizon, as I was telling you before. Here, I'm going to impose a Neumann condition. So you will see later that this works well. So just the radial derivative at the hard wall of the gauge field vanishes. Now, a motivation to take this choice is that if you have a black hole, then if the scalar field condenses, it will have a non-zero value at the horizon. Okay, so if I was imposing Dirichlet boundary condition, I will be fixing the scalar field to be 0 at the horizon, for instance. And that will be a bit different from what you have in the black hole, where you have that the value of the scalar field at the horizon can change. So this looks more similar. Now, you can find normalizable solutions for omega plus q mu different than 0. Yes. Yes, because I'm taking ADS. I'm just looking at solutions that depend on the frequency only. So I'm setting the momentum equal to 0. Thank you. So I'm taking k equals to 0. Ki equals to 0. Because I want to look for homogeneous solutions. So I don't introduce any space dependence. So then, if this is equal to 0, then there is no normalizable solution satisfying the Neumann boundary condition. If this is different than 0, the normalizable solutions look like this. They are Bessel functions, essentially. So there is some parameter, phi m, which is the value of the scalar field at the horizon, some radial dependence, and then you have some Bessel functions, which depend on this combination of chemical potential and frequency. And then I'm introducing some normalization. So this is chosen in such a way that the value of this field at the hard wall equals phi m, this coefficient. Okay, but this is a free parameter of the solution. And you can expand this Bessel function close to the boundary, and then you see that it's normalizable. Now, I have to impose the Neumann boundary condition. So I have to take a derivative of this, and then evaluate it at the hard wall, and then impose that is equal to 0. And what you find is something that in general is non-zero, but it can be 0 for some values of the frequency. Okay, because these Bessel functions are oscillatory functions, then they can become 0 at some particular values of the argument. So you write the frequency as minus the chemical potential, and then you can add or subtract some term. And there is here a number. This is just a number. And this number is determined by an equation of this type. Involving the Bessel functions. And then the condition is that this is different than 0, and then you have a discrete set of solutions. Okay. So this procedure is similar in the black hole. You do essentially the same, but you're imposing different boundary conditions. And in order to find this, you usually have to do it numerically. These numbers, you can put this in mathematics, and it will spit some numbers of order 1. Okay, so here the spectrum, let's take mu equals 0. This will be frequency. Then the spectrum here is real modes. So they are located on the real axis. And there is some separation from the origin, so there is some mass gap. So this is different from the black hole, where these modes will be in the complex plane. Okay, but this is because, well, we don't have anything going through the hard wall. In the horizon, there is matter going through the black hole, and then you lose energy and so on, and this is why this becomes complex. But here, this is real. Now, if you change the value of the chemical potential, these modes will move, right? So you can actually make this the first mode, the one that is closer to the origin, move all the way to the origin. So you have a solution for zero frequency at some critical value of the chemical potential, which is given by this expression. And you can write this in terms of the mass in this way, okay? So at this critical value of the chemical potential, this mode reaches the origin. And this is the equivalent thing to the onset of the instability in the black hole. Now, notice that here these modes won't become complex, so it's not exactly the same situation. There is no dynamical instability. But we will see that it's favored to form a condensate when you have this critical chemical potential. So, okay. Now we want to see the effect of this scalar field on the Gates field. So let's assume that when we reach this value of the critical chemical potential, the system wants to form a condensate, and then the scalar field will be non-zero. And then to leading order is given by this solution, where this mu will be the critical mu. And we're going to take now this amplitude to be small. So it's going to be of order a small parameter epsilon, which is much smaller than 1. Now, the Gates field is coupled to the scalar through the current. So when this is non-zero, there will be a contribution to the Gates field. But because this is quadratic, it will be of order epsilon squared. So there will be a change in the Gates field of order epsilon squared. And actually, this is how people, in the case when you have a black hole, describe the formation of the condensate close to the critical point, doing this kind of expansion. So if you look at the equations for this change in the Gates field, you have a part which is the same as you had before, the homogeneous part. And then there is a contribution that comes from the current. And it's quadratic in that solution. Okay, so this has an analytic solution in terms of an integral. This is, you can solve immediately. And this choice of the lower limit is the one that corresponds to the no flux condition at the horizon. So this is equal to this. Sorry, at the horizon, at the hard wall. And this, with this choice, is equal to 0. So this satisfies the right condition. And then you can integrate this again. So you get another integral, which will be, I'm going to write in this way. Yeah, the hard wall. Yes, sorry. I'm just changing notation all the time. Sorry. But it's always the hard wall. Okay, so the integral of this is this thing, and now I'm taking this limit, this upper limit to be infinity, because then when r goes to infinity, delta I0 goes to 0, so then I'm not changing the chemical potential. So the chemical potential is the one that I had originally over there. Okay, so this is why I choose this in this way. So you can expand this solution or the full solution. If you expand the full solution close to the boundary, then you have the chemical potential, and then there is a term which is suppressed. And it has this dependence, which is the one you expect for a gauge field. And then there is this coefficient, which essentially is the change in the charge density. No? Because when the scalar field is non-zero, it's like having a condensate in the dual field theory, and this means the charge density has to be non-zero. So you can compute this delta Q from these expressions. I can do it here, I guess. So delta Q is given by an expression like this. And then there is this integral that now is between the hard wall and the infinity. And then this becomes something like this. And I'm not going to write this function. It's known explicitly, but it's a bit messy to write. And just it's a positive function. So if you use the definition of the relation between the hard wall and the mass, you find that the charge density at the critical chemical potential just is proportional to this scale that is given by the hard wall. And then you have the field at the horizon, sorry, at the hard wall, and then this function. And this is just these numbers we were finding for the mode. Okay, so now I've seen that I can have a condensate. This will produce some charge density. And I want to see if this really happens, or I will just remain in the state where there is no condensate and no charge density. So for this, I need to compute the free energy of the system. So how am I doing with time? 35 minutes? Okay. So as you have heard from the lectures of Horacio, I think the free energy is given by the Onsel action of gravity. Now there is a part of the Onsel action which is just the Einstein gravity part, which is just ADS with the hard wall, and that doesn't depend on the chemical potential or the charge or anything. So it's just a constant contribution that I can neglect. And then there is another part which is coming from the gauge field and the scalar. And then if you integrate by parts and you introduce some cutoff much larger than the scale of the hardware, then you find that this regularized action is given by, so now I'm going to the Euclidean, and I'm making the time to be compact, just for simplicity, it doesn't matter. And then you have this beta, the volume of the space directions, some factors from the action, and then a contribution from the Onsel action of the scalar, which is coming from integrating by parts the kinetic term. There is only this radial dependence, and then a contribution from the gauge field. And there is some subtlety, because if you want to do the right thermodynamics, you have to keep this minus sign. You could do it also in the Lorentzian, and then the action will be similar, but there will be an extra minus. Now, I wrote the expansions of the scalar and the gauge field before. If you plug them in this action and you expand, then you find, well, there is all these factors. There is first a term that goes like the non-normalizable mode, the square. And it has a dependence on the cutoff that will blow up if you send the cutoff to infinity. There is a finite piece, which is like a cross term between the normalizable and non-normalizable modes. And there is a contribution that comes from the gauge field, and which is proportional to the chemical potential times the charge density. Now, we want to get rid of this divergence. So we can do that following the usual procedure of holographic renormalization. So we will add some term, which is local on a radial slice. And it will have all the right symmetry properties, so it will be invariant under this gauge symmetry and so on. And the term that cancels this divergence is just a mass term for the scalar field. So it will be something like on R equals R lambda, you'll have the induced metric. I will write it in a moment. And then you have a mass term like this. And here there is a coefficient that one has to fix. This coefficient should be such that when we expand this for large R lambda, it will cancel this divergence. So let me just write it. What this is, this will be d minus delta over L beta b d minus 1, 16 pi q squared d minus plus 1 square root of gamma phi squared. Okay. I'm using that nothing depends on time or space, and then this is the overall coefficient, and this is the right number you have to put here, d minus delta over L. So the induced metric is just, yes. Well, mu is not the problem here. The problem is this C1. Yeah, but you will lose this, which is, you need to compute the expectation value of the scalar operator. So you will also kill this finite piece if you subtract for b equals to 0. This doesn't depend on. If you're saying to subtract just this term, then you will get the wrong result for the expectation value of the scalar operator, because this also has finite contributions that affect to this part. So to do it properly, you have to add this term. And in fact, this is originally when Witten did the calculation with the scalar, he just subtracted, and then the result was not the right one. Later, people realized there was a problem. Okay, so the induced metric is just the metric on the radial slice. So this is just r lambda square over L square eta mu dx mu dx nu. And then you plug the expansions and the expression for the induced metric. And you find that this S phi square equals d minus delta over LD plus 1, beta V d minus 1, 16p Q square dD plus 1. And then there is C1 square R lambda 2 delta minus D. So this has the same power. And if you check the coefficients, you see they cancel. And there is an extra finite piece that is the one I was mentioning. So when you add the two terms, and you take the limit of the cutoff going to infinity, you get the renormalized action, which is finite. And then in this case, it's just this thing. So there is this coefficient, which is now 2 delta minus D. Right? Now it's different from what we had there. And there is the contribution from the chemical potential. Okay, so from this on-cell action, we can first extract the expectation value of the scalar operator. We identify this coefficient of the non-normalizable mode with the source for the dual operator, and we need to introduce some factors of the radius to make dimensions work. So J will be the source, and the expectation value is given by the variation of the renormalized action with respect to the source. If delta equals D over 2? Yes, if delta equals D over 2, then the expansion I wrote is not right anymore. There are logarithmic terms. So you have to redo this with the logarithmic terms. So this gives some coefficient. This gives something that is proportional to C2. You just see, if you take the variation with respect to C1, you get something proportional to C2. And then you can use this solution, expanded when R goes to infinity, to read C2. And then after you do that, you get some expression. And I'm going also to simplify the expression by using that in the usual dictionary, this radius to the D minus 1 over the Newton constant, you can identify with the number of colors squared over 4 pi. Okay, so I'm going to get rid of some factors of L and G Newton using this identification. And also, I'm going to use that we are in a limit where the charge is very large to use the probe approximation. And my choice is going to be that this is going to be a square root of n. Okay, this is just a choice I'm making. Just to make these expressions look a bit simpler. So when you use these things, then you find that the expectation value of the scalar operator is n over 64 pi squared d minus 2 delta. There is a factor numerical Then there is the mass given by the hard wall to the dimension delta. So this fixes you see that the dimension of the operator is delta, and this is having the right dimensions. And there are a few other numerical factors. And it's proportional to the value of the scalar field at the horizon. Okay, so you could also use this relation to relate the value of the scalar field at the horizon to the expectation value of the dual operator. Okay, so once I have computed the expectation value, I can compute the free energy in the case of a spontaneous breaking. So this means the source is equal to 0. So I'm left only with this part, the part that depends on the charge density. And then the free energy density according to the usual dictionary is going to be the renormalized action over times the temperature over the volume. So this is given by n over 64 pi squared d minus 2 mu delta q and so there is a minus here, minus n over 32 pi squared L squared md plus 2 Z1 squared g Z1 phi m squared. Okay, I'm using this now at the critical point. So this takes care of the dimensions. Now, it doesn't depend only on m, but there is this L here. And then you see here that it depends on the value of the scalar field at the horizon squared. So from this relation, you see that the free energy is proportional to minus the expectation value squared. So this means, remember that we are doing this for small amplitudes of the scalar field. So this means we are close to the critical point. So close to the critical point is, at this value of the critical potential, is thermodynamically favorable to form a condensate and lower the free energy. Okay? If you plot the free energy versus the condensate, it will look something like this. Now, this doesn't tell us what is the endpoint. For this, you have to do the full nonlinear analysis. Okay? At some point, this might have a minimum, and then this will be the value of the condensate in the ground state. So for the black holes, things are similar to this. Again, if you compute the free energy, you will see that it becomes favorable to form the condensate. And this coincides with the onset of the instability of the quasi-normal modes, usually. And then, yeah. Yeah. Yeah, the temperature is like 0 temperature because I was taking pure ADS. And right. Sorry, say it again. Yeah. Well, because I was taking the the Euclidean and I was compactifying time, but it's like being in the confining phase. Like in the confining phase, it doesn't. Right. It's just to make this some kind of finite thing. Otherwise, I will have here the integral over time. So just for convenience, but it doesn't play any role. But notice that this situation only happens when you have when the chemical potential is at the critical value. Okay, so in general, if the chemical potential is different, there is no normalizable solution that satisfies the boundary conditions at the hard wall. So there wouldn't be a condensate. Okay, so you have to first tune the chemical potential, and then when you're at the critical value, you see that it becomes favorable to form the condensate. So in the black hole, you change the chemical potential again, if you're fixing the temperature. And then there is a critical value where there is a mode that becomes unstable. And then you see that that also coincides with the point where the free energy of the state with a condensate is smaller, is below the free energy of the state without the condensate. And then you can find numerically the solutions. Let's say if you plot here, let's say you fix the chemical potential and change the temperature. And here you plot the condensate. Then you will reach some critical temperature. And at this point, the condensate will start growing. Typically, it has this shape. And here, the usual situation is that this looks like a mean field second-order phase transition. So this means the condensate vanishes as a square root. But there are other exotic models where you can find different exponents here as well, like more complicated. If you keep lowering the temperature here, and you take into account back reaction at very small temperatures, then all the charge of the black hole will be carried by the scalar. And in fact, there won't be a black hole anymore. There won't be a horizon. And typically here you find that the geometry in the infrared becomes something like a Lipschitz or hyperscaling violating Lipschitz geometry. Okay, so this is telling us about the thermodynamics. Now we want to see some superconducting behavior. So we're going to talk a bit about transport. So in fact, we want to compute the conductivity. So we introduce a small external source, some AI of t. And then we can use linear response theory. And the value of the current will be determined by the retarded correlator of the currents contracted with the source. So don't confuse this A with the bulk A. This is something in the field theory. This is an external gauge field. If we Fourier transform, this is just the product of the Fourier transform source and the correlator. And then, as you know, the electric field is the time derivative of this gauge potential. So it's minus I omega times the gauge potential. So you can write this equation in the usual way. I over omega, the retarded correlator times the electric field. And then this is the DC conductivity. So the Kubo formula that relates the conductivity to the retarded correlator is making these two things the same. So we want to compute this retarded correlator and then from it the conductivity. So in order to compute correlators, we need to do fluctuations, in this case of the gauge field, because the gauge field in the bulk is dual to the current. So from the same equations of motion, we get that for the Fourier components of the gauge field, the equations are so this is the 4 momentum along the field theory directions, well, the 4 or D momentum. And then there is a part. Okay, this in the black hole will be more complicated, but in IDS it looks like this. So I'm going to split the gauge field in transverse with respect to the momentum and longitudinal components. And then the transverse component is defined as delta mu nu minus k mu over k squared times a nu. And the longitudinal component is k nu over k squared a nu. Okay? You see, if you add these two, you get this. So this is the usual decomposition. To compute the conductivity, I can focus on the transverse components of the gauge field. So let me call little a and only the space components. And this to make formula simpler. And then the equation for these space transverse components, it takes this form. Okay, so this is d momentums, involves the frequency and the spatial momentum. And we are going to expand for a small momentum. We're interested in the low frequency behavior and zero momentum. So we expand, there is a leading term, and then there is a k, order k squared term, and so on and so forth. You can expand in powers of k squared. So you plug this in this equation and then keep terms of the same order. So to order 0, this goes away. You just have this solution. And it has to satisfy the condition that there is no flux through the horizon. So this is just a constant. That I'm going to put a B of boundary value. Now, at the next order k squared, then you have this term. But this term is multiplying the 0th order term. So this is an inhomogeneous term in this equation for A1. And it's just a constant, so you can just solve for it very easily. So in the black hole, people also use this kind of expansions, usually low frequency expansions, to compute hydrodynamic modes, for instance, or the conductivity at small frequencies. And up to technical complications is the same logic. So the first correction to the gauge field looks like this for the derivative. And again, this lower limit is fixed by imposing the no flux condition through the hard wall. You can do this integral explicitly. And it takes this form. And then if you impose that the leading term is given by the 0th order solution, so the constant term is fixed by this, then that fixes the integration of this to the next order. Sorry, to find AI1 instead of the derivative. And then this is what you find for the solution, 2 order k squared. So notice I'm doing everything. I didn't turn on the scalar field yet. Okay, everything is when the scalar field is 0. Now you have this solution. You have to plug it in the Onsel action, as we were doing before, to compute the free energy. And then you will have something which is quadratic in this ATAB. So then the current correlator is the derivative of the renormalized action with respect to these sources. And then if you do the exercise, you find that it goes like md minus 4 k squared delta j minus ki kj over k squared. So these are the space components of the d momentum. And if you want to compute the conductivity at 0 momentum, 0 space momentum, you divide this by omega, so multiply by I omega ji jj. And then at 0 spatial momentum, this term is 0, and this is omega squared, or minus omega squared. And then you divide by omega. So the AC conductivity at 0 spatial momentum goes like I m d minus 4 omega. Okay. So in the case where the scalar field is 0, you find that the conductivity is going to 0 at 0 frequency. So this is like having an insulator. Okay? There is no DC conductivity. And this is different from a black hole. If you were doing this calculation in a black hole, then if the black hole is charged, you will find this pole at 0 frequency, which is like a perfect conductor. If the black hole is not charged, you still find a finite number at 0 frequency. So there is some finite conductivity in the neutral black hole, which is because you have percreation that produces a non-zero conductivity. But in this case, we have an insulator. So this will be insulator. So what happens if I turn on the scalar field? Well, as I said, when we were close to the critical point, the amplitude of the scalar field was small, of order of some parameter epsilon. And then we can expand the gauge field also in this parameter. So now this thing refers to the expansion with respect to the amplitude of the scalar. So as we know, the first correction is of order epsilon squared. So the solution for the leading term is still the same thing. Some constant. The equations don't change. And the equation for the next order correction is like this. There is the homogeneous part, which is always the same. And then there is a part which depends on the scalar field. And then is multiplied by this value. So, okay, let me take this out. Okay, so we can solve this equation as we did the rest, it works in the same way. And then one finds that the solution for the gauge field is this one. So okay, and these limits are chosen in the same way as before. No? The no flux condition at the hard wall and keeping this fixed. Now, if you expand this close to the boundary, when R goes to infinity, you find here there is a contribution from this part that is suppressed. It goes like 1 over R d minus 2. And then the coefficient is given by this integral of the scalar. Okay, but this looks similar as the contribution we had in the density, but now we are multiplying this by this source for the current. Okay, so if we plug this in the on-cell action, and we take two variations with respect to the source, then we find a contribution to the current correlator, which will be a constant, essentially. So the current correlator will be given by something that is the variation of the renormalization. And this goes like some constant, rho s times delta j. And this rho s is given by an expression like this. Okay, so it depends. I'm going to take, here I'm making a change of variables, rescaling the radial coordinate. But I just took x to be R over Rm. So this doesn't depend on Rm. All the scales are here. Okay, so you see that if this is a constant, then the conductivity is going to have a pole. So it's going to be pi delta omega plus I over omega times rho s delta j. So this looks like the conductivity for a superconductor, and this is the super fluid density, if you want, or the superconducting density. If you do this calculation in the black holes, you will find something like this as well. If you break translational invariance, for instance, so you don't have a perfect conductor in the normal phase, then the only contribution to this pole will be the superfluid contribution. Okay, here we don't have to worry about that because in the normal phase the system is an insulator, so the conductivity was 0. Is over the time? Okay, so I'll stop here. Thank you.